we want to talk about projectile motion. The idea here is that I'm going to throw a ball. I'm going to hit a tennis ball with the racket. I'm going to shoot a rock with a slingshot. I'm going to send something flying that has no motor or anything else keeping it in the air for any length of time, so gravity will bring it down to the earth. Now, the faster something moves, the more we have to consider things like air resistance, and so we're going to come up with some fairly artificial conditions. Now, one of Newton's laws, the law of gravity basically, states really simply that objects of equal mass fall at the same rate. I have two pieces of paper in my hand that are the exact same size, shape, and mass. And we can see that clearly is not true in all situations. In fact, on planet Earth, it's probably never going to be true because that law only applies in a vacuum. So if I don't have a vacuum, as you saw the one piece of paper fall slowly, it's mass and surface area that contribute to this. The idea of a parachute. A parachute will actually slow you down because of the surface area. Now, as you fall faster and faster and faster, you reach what's called terminal velocity normally, which is kind of an oxymoron because it's not terminal velocity, it's terminal acceleration. Kind of like the Bugs Bunny cartoon where he's falling in the airplane and right before they hit the ground they stop because they reach terminal velocity. So the idea of terminal acceleration means you don't speed up any further because the air resistance is equal to the gravitational forces and they cancel each other out. We're going to have a totally artificial condition. We're going to play catch in a vacuum, and we want to describe the motion in its simplest terms. So basically, I send something through the air, it's going to hit the ground. There's no wind, there's no curving through the air. It's going to cut a path on a plane, which means there's only horizontal and vertical movement that I have to consider in this situation. So it's not all that complicated. Now, in previous math classes, you understood that the motion we always used when gravity was the only thing involved came from this simple equation right here, which stated that the position or basically the arc that I've traveled is -1/2 gravity times squared, initial speed times time, initial height. But because we were always going straight up and down, is a fairly simple thing to model. You said how long it was in the air, when did it reach its highest point, things like that. But now we're going to go with an angle. So the idea here is I have a horizontal and I have a vertical movement. So there is clearly then an angle made with my original motion. So this guy here is now broken up into two parts, the vertical and the horizontal. So to describe motion now this way, I have x of t and I have y of t that are completely independent of each other. Now, the horizontal motion is not subject to gravity. It's only subject to the initial speed. So this turns out to be the amount of speed horizontally, which would be v0 times the cosine of theta times time. And this guy here, it's basically the same equation, but v0 times the sine of theta times time, and then plus s0. So r of t, if I'm talking about projectile motion where gravity is the only force acting on it and there's no air resistance, is simply x of t, y of t. Now, to make this simpler, for this scenario here, we're going to use English standard units because then I can use 32 feet per second squared rather than 9.8 meters per second squared. And now we'll do a very simple example. Now, we're going to launch a projectile into the air at an angle of 30 degrees with initial speed of 92 feet per second, 640 feet off the ground. So eventually this thing's going to hit the ground. There's a few questions we have here. First of all, let's get a vector that describes its motion for any time. Let's figure out when it hits the ground. Let's figure out how far away it hits the ground, and let's figure out its speed upon impact. So the first thing we'll find is x of t. X of t is 192 times the cosine of 30 degrees times time. Well, cosine of 30 degrees is just root 3 over 2. So this would be 96 root 3t. Y of t, negative, we will use gravity at 32 feet per second squared. So this will be negative 16t squared plus 192 sine 30 degrees t plus 640. Sine of 30 degrees is just 1/2. So this will be 96t for that term. Now, in this case here, some of you want to go ahead and evaluate square root of t and put in a decimal. That would be quite incorrect. There's an absolute law in math and physics, whether you learned it or not. You never approximate a coefficient in any scenario. You approximate your final answer, but you don't approximate the numbers you use to calculate the final answer, because this is an irrational number, and if I calculate it first, then all of my subsequent numbers will be slightly off. Now finally, we've got r of t equal to 96 root 3t, negative 16t squared plus 96t plus 640. Now let's start answering the rest of our questions. Now with this position vector, the next thing we'd like to know is how long is it going to take to hit the ground? Well, it hits the ground when y of t equals 0, so I need to set this quantity equal to 0. So either using the quadratic formula or just trying to factor this thing, which it does, it factors as t squared minus 6t minus 40, or t minus 10, t plus 4. That gives us a couple of nice answers. Either t equals 10 or t equals negative 4. But since I'm launching the thing, it hits the ground in 10 seconds, it really can't hit the ground in negative 4. So this would be an extraneous solution. So 10 seconds from now, how far away will it move horizontally? So what we want is x of 10, which is 96 root 3 times 10, or 960 root 3. Now, this is the correct answer, but I don't really have a good feel for that size. Later today, when I go to Home Depot and ask for 960 root 3 feet of wood, they're going to look at me like I'm crazy. So we need to calculate this. This is where we do a decimal approximation. And this value would be approximately 1662, let's see, 0.8, let's say, feet. The number of decimals isn't important. It's how many do you need for the problem you're doing. Okay, so now we figured out how far away it lands. The next thing we want to figure out then is how fast is it going when it hits the ground. To find the speed upon impact, I need to find the velocity vector first. So I'm going to take the derivative of r of t, and that will be 96 root 3, and negative 32t plus 96. Now you notice the x component of this vector is a constant. Now why is that? Because the horizontal motion will never change, because it is not affected by gravity. Only the vertical motion is affected by gravity. So it will continue moving at this speed horizontally until it hits the ground. V of 10 would be 96 root 3. If I replace t with 10, I'll get negative 224. This indicates that I was going down before I hit the ground. So I have a tremendous downward value right there. And now finally, we want the length of this vector, which would be the square of this plus the square of this under the square root. And that equals, that's exactly the square root of 77,824. These are integer values, which reduces beautifully to 64 root 19. Most of your calculators will do that for you, except once again, I don't really have a feel for the size of that number, even though that's a correct answer. So this would be appropriate to give a decimal approximation, and we come up with about 278.97 feet per second. Now what's very important to notice about this number here is that this is much faster than our initial speed, which makes sense because we were 640 feet off the ground, launching it at 192 feet per second. When I get back to the same 640 feet off the ground, I should be going exactly the same speed, so now I've had 640 feet to speed up. If this number here is less than your initial speed, that's bad. It means I make a mistake. If it's way, way past it, if I have tens of thousands, then I probably made a mistake. But here's a very basic example of projectile motion that we can now apply using what we know.